It is supposed to be here because here on this the particle here on the left of this point. Let's call this point M. Yeah, let us see. Let us see. Here the particle on the left is having positive displacement, meaning they are moving to the right. In May 2002. Let me erase the note first.
Okay. Oh, so today is the last class, right?
Mm-hmm. It depends on you. If you want an extra session like in this week.
Oh, then can we like do one more time this Friday or like the other day?
Mm-hmm. Yes.
Oh, and also I think I have to go at 9:30 because I have another class. So can we like do extra 5 minutes next lesson?
Mm-hmm. Okay.
Yeah.
Okay.
Yeah, thank you.
I cannot erase the note on this document. Okay, here it is. Let me share the string. There's tab. Okay, paper 2.
Yeah.
We've done this kind of question already, right?
No,
It's
it was different.
2002. Or
Yeah.
you made 2001?
Oh no, this one.
Mm-hmm. I remember like we've done this one.
I remember that we haven't finished all.
Okay, Jamboard. You study another subject very late, like 9:30.
Yeah.
What's that subject?
It is math.
Mm-hmm. This is a link to the board.
Okay.
Write the solution on it, okay? Address leave the racket speed. What is the speed of the tennis ball when leaving the racket? What's the mass of the ball? And the time of the contact between the ball and the racket. Calculate the average force. Force is mass multiplied with acceleration, huh? And then you need to calculate acceleration, which is final velocity, subtract initial velocity, and then divide time. Mass time acceleration. Acceleration is the change in velocity. The initial velocity is 0. The final velocity is 64. And then divide the time. You need to convert the time from millisecond to millisecond. Yeah, millisecond to second. Multiply with 10 to the power negative 3.
And when do you have the time on Friday or another day for extra class?
1 minute. Check my schedule.
Oh, okay.
8 p.m. on Friday.
Oh, yeah, sure. I'm okay. Yeah, I will do it on that time.
Okay, and then you can round to two significant figures, which is 150.
Okay.
The masking. Yes, 150 newtons. Question 2. Average power. Power is energy divided by time, but what it means by average? Why it is called average? Because the speed increases from 0 to 64, but we don't know how it increased. For example, this is the graph of the speed, and this is the time. We don't know if it can increase linearly or exponentially.
Yeah.
There's the equation in the booklet. The power is the force multiplied with the speed.
Yeah.
This is the average force. Okay, so we can take that average force multiplied with the speed, but this equation actually applies for the constant speed. But in this problem, the speed varies from 0 to 64, not constant. There's another way to calculate power, which is energy over time. Energy is the kinetic energy 1/2 mv squared divided time. But I wonder if we need to take like average velocity or the maximum velocity 64 here. We'll check my skin. Yeah, they use the energy over time and use the 64. Wow, this should not be called average. Huh? This is like the maximum power. Not exactly, because the power varies with the energy, because the velocity varies. It's not a constant velocity.
Yeah.
Okay, so just use the kinetic energy and divide the time. Again, the formula, the power equal to the force multiplied with the speed, is only applicable when the speed here is constant.
4,750.
Yeah, 4,700. Yeah, it is correct. The next question on the next page. Given this thing, the initial height of the ball, the angle 7 degrees that the ball makes the horizontal direction, the distance 11.9 meter from the ball to the net, and the height of the net. Question 1, calculate the time taken for the tennis ball to reach the net. Can you do that? You just need to take the horizontal distance here, 11.9, divided by the horizontal speed. The speed here, 64, is the initial velocity, not speed. You can resolve that velocity into two components: horizontal velocity Vx and vertical velocity Vy. Okay, Vy. Horizontal velocity is V64 here, multiplied with cosine of 7 degrees. Cosine 7 degrees. And Vy is 64 times sine of 7 degrees. Okay. The time here, you just need to take the horizontal distance, which is 11.9, and divide the horizontal velocity, Vx. Okay. 2 marks. So the first mark, you calculate this Vx, and then the second mark, calculate the time. And round that result to 2 sigma. Yeah, 0.18. Yeah, 19. The answer is 19, 0.19.
Yeah.
Okay, that's the time.
Okay.
The next question 2. This kind of problem is called projectile motion. Projectile motion problem. The next one. Show that the tennis ball passes over the net. To prove that thing, we need to prove that the height of the tennis ball, the height at the moment, at the time here, 0.19 second, must be greater than the height of the net. The height at that moment, 0.19 second of the ball, must be greater. We need to prove that it's greater than the height of the net, which is 0.91. 0.91. Okay, and this height of the ball is calculated by the initial height, 2.8 meter, subtract the distance s that the object falls in 0.19 second. Okay, this distance s is calculated by the formula ut plus 1/2 at squared. Okay, where u here is the initial vertical velocity Vy, which is 64 times sine of 7 degrees. Okay, that is u. Yes, vertical initial velocity. The time t is 0.19 second here, and acceleration in this formula actually g, gravitational acceleration, which is 9.81 meter per second squared downwards. Okay.
Yes.
Use this formula, calculate the distance it falls in that time, and then take initial distance, subtract that distance, you get the height at that moment, and it will be greater than the net, the height of the net. Okay.
Yeah.
To remark, so the first mark, write the distance, calculate the distance that the ball falls in 0.19 seconds, and note that you should replace the value 0.187 something to be more accurate, 1873. Okay, the distance that the ball falls in that time, the vertical distance the ball falls in 0.1873 seconds, or you can round to 19 seconds. That's the first step. And then the second step, the height of the ball at the time, 19 seconds. Okay.
Yeah.
And finally, the conclusion. Or you can involve another, the first step, calculating the vertical initial velocity, which is 64 times sine of 7 degrees. Okay. Probably those things.
Yeah.
Okay, this is the formula. The second one, s equal ut plus 1/2 at squared, is used to calculate the vertical distance.
If I use the first method, I have to find the vertical
Initial velocity.
initial, the
Yeah.
Vy, right?
Yeah, Vy, which is 64 times sine of 7 degrees.
Yeah.
Do not round the beginnings, the middle steps, only round the final step.
Yeah.
So you can even combine the step like this. Calculate the height. That height is the initial speed, initial height 2.8 meter, and subtract the distance, which is 64 times sine 7 degree, and the time 0.19, 0.187, and then subtract also. You can put it in the bracket. Okay, subtract also 1/2 of g 9.81 times t squared 0.187 square, and this height will be greater than the height of the net, which is 0.191. So you can write one single equation like that to avoid roundings many times.
1.17, so 1.2.
Yes. 1.2.
Yeah.
Greater than 0.91, the height of the net, and therefore we can conclude suddenly that the ball flies over the net, the unit meter, and then finally write a conclusion. So because the height here is greater than 0.91, so the ball flies over the net. Okay. Question 3. Determine the speed of the tennis ball as it strikes the ground. In this projectile motion, the horizontal speed does not change. Vx is a constant, which is 64 times cosine of 7 degrees. Okay. but the Vy, the vertical component, will increase by the formula, the initial velocity u, which is 64 times sine of 7 degrees, and then you need to add it with the acceleration 9.81 multiplied with the time, this formula, okay? And you need to calculate the time here, the time that the tennis ball flies from the racket to the table. To calculate this time, you use this formula, the third one, okay? We don't know the velocity. We know the height. No, not using this one because we know the height. Okay, use this one, the second one here to calculate the time. S is the height, which is 2.8. S here is 2.8 meter. Okay, and U here is this one, 64 times sine 7. Then you can calculate the time and put the time in here to calculate the velocity. Wait, let me think. Yeah, there's another way to calculate this velocity without, doing two steps, calculating the time first. We just need one step. Then we can use the third equation here. S is 2.8 meter. Okay, S, so that you can calculate the final velocity. This is the vertical component. Okay, the velocity has two components. Horizontal component Vx, which is constant, and the vertical component Vy, which increases over time with an acceleration of 9.8, free fall acceleration. Okay.
Yeah.
So you need to calculate the vertical velocity when it hits the table using the third formula here. Okay.
Yeah.
And then finally conclude that the final velocity, the final speed, is the square root of Vx squared plus Vy squared, Pythagorean theorem, because the two vectors Vx, Vy are perpendicular to each other, and the total velocity is the sum of these two vectors in this direction, V total. Okay, the diagonal, the hypotenuse of the right triangle. Okay.
Yeah.
You use the third formula here to calculate the Vy.
Yeah.
Do that. The x is constant there.
No.
Use the third formula here. Calculate the vertical velocity.
Here. I'm a little bit confused. Can you help me?
Let me find a picture. Projectile motion. Horizontal. Velocity. Okay, yeah. Let me use a GeoGebra. Okay, this like this one, huh? Yeah. The velocity of an object. Do not care about the first half of this path. We assume that that it started from the top here, thrown with the initial velocity 7 degree. Start from here, huh? From here, 7 degree to the horizontal. The green arrow here is the horizontal velocity. The blue arrow is the vertical velocity, and the actual velocity is the black arrow here. The two components, Vx and Vy, actually the components from the actual velocity, the black arrow. Okay, like we initially did analyze a result velocity, the initial velocity making an angle like 7 degree here. A little bit greater, 7 degree. Okay, because of the effect of gravity, the gravity pulling the ball down, providing the ball an acceleration which is 9.8 meters per second square. The vertical velocity will increase. You can see that here. The green arrow is increasing in the length, increasing in the magnitude of the vertical velocity. Okay.
Yeah.
The horizontal velocity, the green arrow does not change the value because there is no horizontal forces. We ignore the air resistance. Therefore, there is no acceleration in the horizontal direction. Horizontal velocity is constant, which is 64 times cosine 7 degree here. Okay. But the vertical velocity, you need to calculate that vertical velocity at the instant that the ball hit the table. The ball starts from here, hit the table down here. It takes some time, but we don't know the time. And therefore, we can use the third formula here to calculate the vertical velocity when it hit the table here. This vertical velocity, Vy. Okay?
Yeah.
The initial velocity in this formula, U there is 64 times sine 7 degree here. Initially, it does not start like horizontally like that. Okay, the initial velocity here, and then you resolve that. You see the U vertical initial velocity, this value. Okay, and then plot it with 2as equal to v squared. Use this formula to find this Vy. Okay, that Vy is the square root of U squared there plus 2as. Okay, A is 9.81 free fall acceleration meter per second square. Okay, and S here the distance, which is the initial height, which is 2.8 meter. 2.8 meter. Okay, S is 2.8 meter. So calculate Vy here first, and then because the two velocities are perpendicular to each other, the actual velocity is the hypotenuse of the right triangle here, and therefore we can use the Pythagorean theorem. V total is the square root of Vx squared plus Vy squared. Okay.
Yeah. Okay.
Okay, so calculate that vertical velocity first. Use the third equation here, calculate the vertical velocity. There's another way. Let me try explain that second way, and I think that will be easier than the first way. You can use the conservation of energy, okay?
Yeah.
Of energy. The kinetic energy of the ball at the top is 1/2 of m times initial velocity, which is 64 squared, and then you add it with potential energy mgh, where h is 2.5 meter. Okay, the initial height, and then it will equal to the mechanical energy when the ball hit the table, which is only 1/2 mv final square, because the potential energy is now 0. Okay, zero potential energy. So just solve this formula. You can simplify M also, huh? So this formula you can get V directly. Wow, this is a lot faster and easier to understand compared to this way, huh?
Yeah.
Yeah, do the second one.
Okay.
On the next page here. I erase it.
But I already solved it.
So where? Here. Okay,
Yeah.
64.4. Show these, the detail, the work, huh?
Yeah.
Here, 64.4. Okay, anyway, there's a second way here, huh? You
Yeah.
can check it later. You get the same velocity.
Okay.
Question 2. Wow, question C here. You can skip it because it's not going to be reappear.
Yeah.
Because it's the kind of recent paper. But the projectile motion question is kind of typical, meaning it appears many times in the past paper.
Yeah.
Okay, question 2 about thermophysics. Can you do that? Estimate the average speed of the helium atom in the container. The question is the speed, so you need to look into the formula booklet to find the formula of the speed. Actually, it does not show, obviously, but implied in the here. You give this one. We are given the pressure, the volume, the temperature, okay, and the mass of helium atom. From that temperature, you can calculate the kinetic energy here, EK average. This is the average kinetic energy of one single molecule, okay? Using, you can, ignore the second equation, just use the first one here. I mean, this one. Just do not care about this one, second one, okay? KB here is called the Boltzmann constant, and you can check in the book the value in the booklet. Calculate that kinetic energy, EK average, okay? And this kinetic energy can be calculated also by another formula, which is 1/2 mv squared, where Vm here is the mass of one single molecule, which is given here 6.6 times 10 to negative 27, huh? Okay, and so that equation with the known values to get the average speed.
Yeah, 1,470.
And you can route to sig fig, which is 100 and 1,400. It is pretty high, and it is normal because this is the normal speed of the molecule with this very high temperature, 320 Kelvin. It just we cannot see those molecules because they're tiny, okay?
Yep.
And the density of these molecules are very low, and therefore we do not feel much effect the hot temperature, okay, of the gas. And yeah, comparing to the mass scheme, it is correct, 1,400.
Yep.
Question B, show that the number of helium atoms in the container is 4 times 10 to 22, 10 power 20 here. You just need to use the PV equal nRT, the first equation in the topic, to calculate n, and then multiply that n with the Avogadro number. Search the value in the booklet, 6.02 times 10 to 23. Multiply the number of mole, and with this Avogadro number, you get the number of the atom.
Three times 10 to the 20.
Yes. Oh, wait. The value in the problem is here 4. Pressure, Pascal, okay. Temperature, PV, volume meter cube, okay, over RT. Kelvin. The number of mole.
Oh, yeah. I got 3.7 times 10 to the 20.
3.7. Okay,
Yeah.
3.7. So that
There
very
was
close. Yeah.
miscalculation.
A helium atom has a volume of 4.9 times 10 to minus 3.1 meter cube. Calculate the ratio of volume of helium atoms and the volume of helium gas. Volume of helium atom over helium gas. The volume of the helium atom on the top is the number of the atom, which is 3.7 times 10 to 20. You multiply with the volume of one single atom, which is a sphere. Therefore, the volume of that atom is 4/3 sphere. Pi times r cube. R is the radius. Do we know that radius? No, we don't. Atom has a volume. A helium atom. Oh, okay. We don't need to calculate that. It is given here. Multiply that with 4.9 times 10 to minus 31. Okay. Let's see the volume of all the helium atom, 3.7 times 10 to 20 atoms. Okay. And then divide the volume of helium gas, which is this volume, 3.2 times 10 to the 6. Okay. 3.2 times 10 to the 6. This is the ratio that we need to find.
Yeah.
Okay. I raise it, do it again.
Yeah.
Wait. You need to multiply the number of the atom, 3.7, not exactly 4 here, change this to 3.7, and multiply this number of atoms with the volume of one atom, which is this one, not this value.
Oh.
Volume of one atom. And then here, the bottom is the volume of the whole gas. The volume of the occupied by the gas, which is 3.2 times 10 to the 6. Are you okay? I mean, your health? Like you feeling normal or stressed?
No, I'm okay right now. Not really that like stressed, like I will die soon. Because like my university is finished. It is 5.6 times 5.7 times 10 to negative 5.
Yeah. Very close to the answer. 6.
Yeah.
Yeah. What does it mean? A very small number. It means that the total volume of the atoms, 3.7 times 10 to 20 atoms, the total volume is very small compared to the entire volume occupied by the gas, which means there's a lot of space between these molecules. Okay. Meaning the molecules are very far away from each other. The density is very low. This ratio means that thing. Okay. Question 2. Discuss by reference to the kinetic model of the ideal gas and the answer to C1 whether the assumption that helium behaves as an ideal gas is justified. The answer is yes, this is helium gas behave like ideal gas because the ratio in C1 is very small, which means that the molecules are very far away from each other. The density is very low. That is the most important assumption for ideal gas. Okay?
Yeah.
Yes, it is ideal gas because the ratio in C1 is very low, implying that the volume of the atom is negligible compared to the total volume of the gas occupied by the gas. The density is very low. Justified. Negligible compared to the answer in C1. No. I don't know why you didn't remember. think I just explained. The ratio, let me increase the size. The ratio above, the ratio in C1 is very small which means the volume of the atoms are negligible compared to the total volume occupied by the gas, which means the molecules are the atoms live very far from each other, low density. Okay, so the helium gas is ideal. Okay.
Yeah.
Summarize that. Make it shorter. The most important assumption of ideal gas is low density. Ideal gas means low density and also low potential energy. Only the kinetic energy that matters.
Does the pressure affect the ideal gas?
The pressures can be normal, not very high, but not very low. Most importantly, the density. And the particle, the temperature is not too low. That the other condition is the not too low temperature, so that the kinetic energy is a lot greater than the potential energy. A sound wave traveling from metal to the air. The particle P here in the metal sheet performs simple harmonic oscillations. With the displacement of the particle P here is 3.2 micrometer. The magnitude of this acceleration is 7.9 meter per second square. Calculate the magnitude of the acceleration of P when the displacement is 2.3 meter per micrometer. So we have two things, displacement and acceleration. So you need to look for an equation involving those two things, acceleration and displacement, in the formula sheet. This is simple harmonic oscillation, so it's supposed to be in topic 9. And the formula involving those two things, acceleration and displacement, is this one. A here acceleration, X here is displacement. Okay? And omega here is called the angular frequency, and it is given by this equation, 2 pi over the period of the oscillation. Okay? It's called angular frequency. Okay? So according to this equation, the acceleration is proportional to the displacement, which means when the displacement decreases by like 2 times, halved the displacement, the acceleration will also halved. Okay? In this case, it's not half, but the displacement increases from 3.2 to 7. Decrease from 3.2 to 2.3. Let's switch in the digits. Okay, just use that formula. State that the acceleration is proportional to displacement, and therefore we can calculate the new acceleration. A is minus omega square x, meaning A is proportional to x. So we have A1 over A2. A2 is what we need to find, okay? Because it's proportional to x, so it is equal to x1 over x2. x1 is 3.2 micrometer, x2 is 2.3, and A1 is 7.9, already given. And therefore you can calculate A2. Okay?
We have to like think about the omega, or just
we can skip that omega, because actually you can calculate omega because you have already that A1 equal to minus omega squared times x1. A1 is 7.9 equal to minus omega squared times. You can also ignore the negative sign. Okay? We are dealing only with the magnitude of the acceleration multiplied with x, which is 3.2 micro, and therefore you need to times it. But it's longer. It's not necessary to do that, huh? Just use the proportionality.
Yeah.
Yeah, just use the proportionality. Mention one sentence that the acceleration is proportional to the displacement, or you can write the formula a equal to omega squared times x. Okay, so H2 will be
5.7.
Yes, 5/7.
Yeah.
Question B. The way incident at the point Q on the boundary between metal and air, the wave makes an angle of 54 degrees with the normal at Q. The speed of the sound in the metal is 6,010 meters per second, and the speed of the sound in the air is 340 meters per second. Calculate the angle between the normal at Q and the direction of the wave in the air. It is the other way, different from the light. Remember the light, using a laser light and project that from the air to the water. Okay.
Yeah.
This is the incident angle I. In the air, the laser travel faster. In the water, it's travel more slowly, and therefore the refracted angle R here is smaller than the incident angle. Okay. This is for the light. But for the sound, it is the opposite way, because from the metal here going to Q, in the metal the sound travel faster. Yeah, meaning similar to the air here, huh? Okay, travel faster, and then refract out to the air. This angle is 54 degrees. Yeah, also faster. And in the air, the sound travel more slowly. Yeah, so the angle, yeah, it will be the same, meaning it will be smaller also, huh? This angle will be smaller than 54 degrees. Okay, physical refraction.
Yeah.
And we use a formula. Let me check if it's given. I think so. It is given also. Refraction in topic 4. Here, this one. You that one, huh? Theta 1 is 54 degrees. Theta 2 is what we need to find. Okay. V1 in the middle, which is 6,010, and V2 is the air, 340. Okay. Use that formula. I erase this thing, huh? Oh, just keep it there. Go to this page 9. Use this formula in the booklet. Find the angle theta 2, the refracted angle when the sound travel to the air. Okay.
Yeah. I think my Wi-Fi is not working
now. Click refresh page. Theta 2 is the angle we need to find. Theta 1 is 54 degrees.
Yeah.
Convert your calculator into degree, huh? Not radian.
Yeah.
And V2 is in the air, which is 340. V1 is in the metal, which is 6,010. And then use the inverse sine, huh? Function on the calculator to find the angle. And it's supposed to be smaller than 54 degrees. I don't think it's that tiny. Oh, it's correct. 2.6 degrees. Okay. Okay, 2.6 degrees, huh? And yes, that is correct already. The next one about wavelength and standing wave. The question C about wavelength, very simple. The frequency of the sound wave in the middle is 250 Hertz. Determine the wavelength of the wave in the air. Very easy. Wavelength lambda is the speed of the wave in the middle, which is 6010 meters per second, divided by the frequency 250. Okay. Wait. The question is the wavelength in the air, not in the middle. So the speed in the air 240. The wavelength is the speed 240 divided the frequency 250. Okay.
Yeah.
The formula of the wavelength is a familiar one. We've done it many times, huh?
Mm. 1.4 meter.
Yes. And question D. The sound wave in the air enter the pipe that open at both ends. The diagram shows the displacement at a particular time. The standing wave that is set up in the pipe. A particular air molecule had its equilibrium position at the point labeled M. On the diagram at the time t, draw an arrow indicate the direction, the acceleration of this molecule. Draw an arrow indicate the acceleration of this molecule, meaning this acceleration is to the left or to the right, because sound wave is longitudinal wave. Sound wave is longitudinal, which means the particle of the air oscillate horizontally in the pipe, left to right, okay, in the same direction with the direction of the wave. I'll show you that standing wave, huh? Standing wave tip GeoGebra. Yeah. Busy with. Okay, let's see if we have like two open ends. Or this one, yeah. We have two open ends, huh? Run. I need to change the length of this tip also, yeah, so that it makes a second harmonic of standing wave like this. Second harmonic, huh? In this problem, is the 1, 2, 3 third harmonic. Okay, to have the third harmonic, I need to change the wavelength here also. Okay, like this. Okay, yeah, this is the third harmonic. A bit okay, beautiful. Now the wavelength decrease a little bit, length of tip decrease a little bit like this. Okay, we see the standing wave in the tip. Note the movement of these particles. Only one particle. For example, our problem, the particle M here. Okay, it's supposed to be here. Here, you see, it is moving to the right along my mouse pointer. Yeah. Okay, now moving to the left again. This is the direction of velocity or displacement here. But each particle here is performing simple harmonic oscillation, and therefore we have a relationship between acceleration and displacement, which is A equal minus omega squared times x, the equation that we've used earlier in the previous question here. So this relationship, the negative sign here, means that the acceleration is out of phase with the displacement with x, meaning if x is to the left, the acceleration will be opposite to the right. Okay? Okay.
Yeah.
Displacement of the point M here is positive displacement, and positive displacement means that the particle is moving to the right. meaning it is moving to the right. And therefore the acceleration must be opposite, meaning to the left. Okay?
Yeah.
So the acceleration must be to the left. You need to draw an arrow like this. Okay? Not easy, right?
Yeah. It is confusing.
Yeah. You see the illustration here, the curve. At the point M here, the curve is on the top side above this horizontal dashed line, meaning it is having a positive displacement. Positive displacement means the particle is moving to the right. Okay? And therefore, according to this formula, the acceleration is in the opposite direction to the displacement, and therefore acceleration is to the left.
Yeah, okay.
Luckily, this kind of problem is very rare. Question 2. Label with the letter C a point in the pipe that is at the center of compression. It is supposed to be here because here on this the particle here on the left of this point, let's call this point M. Yeah, let us see. Here the particle on the left is having positive displacement, meaning they are moving to the right. Okay, and the particle here on the right of the point C having a negative displacement, meaning they are moving to the left, and therefore the molecules are approaching each other from the two sides, left and right. And therefore this point C is a compression center. Okay.
Then is the point right next to the M is the rarefaction?
Here, you mean this point?
Yeah, it is.
Yeah, exactly. Yeah, let's call that is like rarefaction R, Yeah, rarefaction R, because the particles are moving away from each other here. We are concerning about this point, Here, you see, the particles are close to each other here. See, negative to positive displacement. No, this is a way positive here, and negative way. Let me let it running. Okay, no, here, this diagram below. Here, this point. Okay, but this point is not this is a rarefaction, not compression. Compression is here, which means the particle here is moving to the right, but it's weirdly has a. Let's check the mark scheme anyway. See here, yeah. So this is like a wrong illustration, Okay, it is C, definitely this point. Okay.
Got it.
On the left is positive displacement, meaning the particle is moving to the right. Okay, you got it?
Yep, I got
it. Next one, airplane Doppler effect. Okay. Long time no see. Doppler effect. So just use the formula of Doppler effect. The airplane is flying away from the observer, and therefore the frequency will be lower. Okay, use the formula here, Doppler effect in topic 4. Where is that? No, it's not given here. Wow. So if you want to do that problem, Doppler effect, you have to memorize an equation which is not given. That formula is the Doppler frequency collected by the observer, okay, will be equal to the original frequency emitted by the airplane, which is this one, 2,500, okay, divided by, multiply with the speed of the sound, which is 340, and divided by the speed of sound, subtract or minus. When the sort of sound is moving away, the frequency is lower, and therefore we need to add the speed of the airplane, which is 220, 80. Okay. When another thing sort of sound like a car approaching the girl, the frequency will be higher, meaning we do the subtraction instead, not the addition. Okay, but in this case, the airplane is moving away, therefore we need to subtract the bottom. This is the formula of the Doppler effect and not given in the booklet. It's been quite a long time that it hasn't appeared, so it's worth, trying to memorize.
Okay.
Okay, it's right there. Initial frequency multiply with 340, divide that addition.
$1,371.
Yes, the answer is 371, exactly that one, huh?
Yep.
Which is can be rounded up to 2 1,400.
Yep.
Frequency unit hertz, Hz, Hz, Z. Okay. The next one, electricity. Usually with a typical problem that is very likely to appear. Question 5, electricity. Do you worry about paper 3?
Yeah.
We haven't practiced a lot, only a few sessions for that paper 3. Identical light bulbs X, Y, and Z, each of resistance 4 ohms, connected to the cell of the EMF 12 volt. And the cell had negligible internal resistance. The switch is initially open. Calculate the total power is within the circuit. Power, topic 5, electricity. Look for the formula power. Here. Which one among these formula that you think is suitable to use in this problem? Power, what do we have? Resistance, and EMF. Because internal resistance is 0, the EMF is equal to the voltage. And we also have the resistance, and therefore the power, we should choose the formula V squared over R among the 3. Okay, VI, I squared R, and V squared over R. Choose the third one.
Yeah, so is the total resistance 8 ohm?
Yeah, exactly. Yes, R is 8.
18 watts.
Okay. Question B, the switch is now closed. State without calculation, the current in the cell will increase. Why the current increase? When the switch is closed. Because when the switch is closed, the resistor X is connected in parallel with the other resistor Y and Z. The parallel connection will reduce the resistance, the total resistance of the circuit. Okay?
Yeah.
Reduce the total resistance of the circuit. That is one way that we can answer this question. The second way, which is not really official, is saying that because they're connected in parallel, the LiPo X will draw more power, consume more energy from the battery, and therefore the battery must provide a greater current. Okay, this is the X parallel with Y and Z, reducing the resistance of the circuit.
Yeah.
Okay. You do the ratio of the power distributed in Y when the S open and when the switch S is closed. The next one is here. Note that the question is the power on Y only, not on the whole circuit. Okay. And we can use the formula V squared over R to calculate the power, or I squared times R. To save the time, I explain it. In Y, because when the switch is closed, they are parallel, and therefore the voltage applied to Y here will be 6 volt. The voltage applied to Z also 6 volt because they are identical light bulbs. Okay, 6 volt and 6 volt. So that the sum 6 plus 6 is 12 volt. Okay, and it is also 6 volt when the switch is open, meaning the voltage applied to the light bulb Y does not change. V here does not change, and therefore the power also does not change, and therefore the ratio here is 1. Okay. So you just need to write the explanation like 2 sentences. The voltage applied to Y does not change when the switch is open or closed, and therefore the ratio of the power is 1. The power, mentioning the formula of the power also, P equals V squared over R, and therefore the power also does not change, and the ratio is 1. The voltage applied to Y is the same in both cases, the switch open and closed. The ratio, yeah. Well, very long question. Next one, C2, C3 here. The cell is used to charge a parallel plate capacitor in vacuum. The fully charged capacitor is then connected to an ideal voltmeter. The capacitance of the capacitor is 6 microfarad, and the reading is 12 volt. Calculate energy stored in capacitor. You can check the formula of energy in capacitor, which is 1/2 CV squared. C, the capacitance here, and V is 12. And this formula, the tip to remember that it's very similar to kinetic energy 1/2 mv squared. Convert the microfarad to farad, multiply with 10 to the power negative 6 micro. It is microfarad.
Yeah, 4.8 times 10 to the negative 4. Yeah.
The energy can be very small because the capacitance C is so small. It's just microfarad, a tiny capacitor.
Yeah.
Tiny capacitor. Question D. When fully charged, the space between the plate of the capacitor is filled with a dielectric with double permittivity of vacuum. Calculate the change in energy stored in a capacitor. The formula for the capacitance in topic 5, is that? Not even here. Capacitance, I don't think it is in topic like 8. Capacitance. That's so weird. It's not given here. How about topic 11? Oh, okay, I remember now. It is in topic 11. Yeah, this one. I'm looking for this one, topic 11. This epsilon here is the permittivity of the dielectric. Dielectric means an insulation. Okay, it does not the electric current to run through, like glass or vacuum or rubber. Okay.
Yeah.
So, according to this formula, the capacitance C is proportional to that permittivity, and therefore, when replacing the dielectric here by another dielectric with double permittivity, the capacitance will be double. C is double because C is proportional to epsilon, the permittivity. Okay.
Yeah.
But the voltage is not the same. The voltage is not 12 volt. The voltage will be changed. The only thing that is the same on the capacitor is the charge Q. The charge Q is the same.
Yeah.
And the charge is determined by this formula. So Q is capacitance multiplied with V. Okay?
Yeah.
The charge is the same. Q. Same charge. Q equals C times V. So now C is double. 2C. For the charge to be the same, the voltage must be halved. So that 2 times 1/2 is the same. Okay.
Yeah.
Therefore, the voltage now is halved automatically. And therefore, the energy of the capacitor, 1/2 of the new capacitance 2C, but the new voltage V over 2, so where the new energy will be lower. Okay.
Yeah.
Will be half of the initial energy, will be halved. Half the energy. Okay.
Yeah.
The reason for that, the decrease in energy, is the answer to the next question. Why the energy is lower now? Because the energy is used to resist, to oppose the work done to change the dielectric, bringing the old dielectric out and replacing it, inserting the new dielectric to the capacitor. Okay.
Yeah.
The energy is lost to oppose, due to the opposition, to oppose the work done to insert the new dielectric. Okay.
Yeah.
So most students will not be able to answer this one. Just lose 1 mark. It's negligible. Okay.
Yeah.
Okay, so we stop here today.
Okay.